we will look into superposition of waves. And the definition for superposition principle state that if you have two solutions to the wave equation, which is this one here that relates the second derivative respect to space of a disturbance to the second derivative with respect to time of the disturbance, then the linear combination of both of them would also be a solution to this wave equation. And the resultant displacement will be just a simple sum of the two constituent waves. So for electromagnetic wave, we can then represent psi by the electric field or the magnetic field. So you find that just a simple linear combination of the field from wave 1 and the electric field from wave 2. However, this does not apply to nonlinear effects when the light is of very large amplitude. For example, when you use high power laser. In general, you'll find that the orientation of the E and B fields is important because the superposition of orthogonal fields will be different from that of parallel fields. At the moment, we shall treat the electric field as scalar quantities, which is valid if our electric vectors are almost parallel. Let's look into superposition of waves of the same frequency. So we consider two harmonic waves of the same frequency, but they may have different amplitude and phase. So we have E1, which is traveling in this direction, and E2, which is traveling in this direction, and they meet at point P. Now, this is drawn exaggerated when in actual fact, the direction S2 and S1 are almost parallel. We then represent these two waves by the cosine function, where this E01 is amplitude for wave 1, and cos ks1 minus omega t plus the initial phase, which is over here. You can see this space here and this space here is of different width. So the initial space for wave 1 and wave 2 will not be the same. S1 and S2 would be the directed distances from the reference plane to the point where they interact. To simplify, we will then use constant phase, that is, we will then group Ks1 and Psi1 and represent that with alpha 1, Ks2, Psi2 with alpha 2. And now we can rewrite that in these two expressions here. These two waves, when they interact in P, they will differ in phase, and the difference in phase will just be given by the difference of alpha 2 minus alpha 1. And that's just Ks2 plus Psi2 minus Ks1 minus Psi1. Okay, whereby when we group into this form will give us the path difference, whereas this difference of Psi2 minus Psi1 will give us the initial phase difference that is here. So if you use the principle of superposition, the resultant electric field at P would then be adding the two, and that would just be simple addition of these two, since we are considering them as scalar function at the moment. And what would result from it? Well, we can look at two extreme cases. That is when we have total constructive interference where they build up and total destructive interference where they cancel each other. Let's look into total constructive interference. The two individual waves are superposed and they are sort of in step. So as you can see here, the peak of E1 matches with the peak of E2. When it is 0, E2 is also 0. When E1 is at minimum, E2 is also at minimum. So when you add the two of them, they sort of add up, and the amplitude will just simply be the amplitude of E1 add on to the amplitude of E2. And when does this happen? Is when there's a phase difference between the two waves in multiples of a full wave, which is in even multiples of pi. So this difference will be even multiples, so 2m pi, where m is an integer. And the resultant wave, well, we can then write them as in this form, whereby in the second wave we add a 2m pi there, and you will find that adding 2m pi will still give you cosine alpha 1 minus omega t. So in other words, this becomes the common factor, and we just add the amplitude. Now, when they are out of step, totally out of step, for example, if you look at this, in this case, we have two waves which are totally out of step, but they are of different amplitude, where this amplitude is larger, this is smaller. So when E1 is at its peak, E2 is at the valley, but when they're zero, they're still zero. So when they're totally out of step, but amplitude is different, so what we have as a resultant would be also a harmonic wave, but the amplitude would be this amplitude minus this amplitude, all right? So that gives us the difference in amplitude written in this form. And this resultant wave would then be in step with the wave that has the larger amplitude, which is here. You can see the peak coincide with the peak of E1. And when does this happen? It is when the difference in phase between the two waves are odd multiples of pi. We can write that as 2m plus 1 pi over here. The resultant wave, which is to add the two waves, then by including the 2m plus 1 pi to the second wave, and that would result in cosine alpha 1 plus 2m plus 1 pi minus omega t is equivalent to minus cosine alpha 1 minus omega t. So we then have this written in this form, whereby the difference is only in the amplitude. Now, what happens when the amplitude are the same? What do we have? The resultant would be totally zero. If those two waves are not in step, and if they're not totally out of step, meaning that if you look at this reference, now the second wave and the first wave, the peak do not coincide, so they are not totally in step. And if you look at this peak and this valley here, they also do not align, so they are not totally out of step, so they are in between. So when that happens, the resultant amplitude would then lie between the sum of the two individual amplitudes, and it will be larger than the difference between the two amplitudes. And if you look at the resultant here now, the phase does not match that of 2, neither does it match that of wave 1. So they are not in step with either of the waves. Now, in order to describe it in mathematical form easily, then we use complex notation now. For the resultant wave amplitude, then we just take the real part. So here we write as the real part of the sum of the two waves is written here. There is this common time component here, exponential negative I omega t. So we factor that out, and that will leave us with only the phase. This we can represent as a sum, which is E0, which represents the resultant amplitude, and the phase of the resultant wave. So how do we represent this? We use phasor diagram. And what is a phasor? It is a phase vector. In other words, we are actually describing it by representing it with an arrow, as you can see here, whereby the length of this arrow is representative of the amplitude of the resultant wave. And here, the angle that this arrow makes with the horizontal, phi here, is actually the phase. And we then can resolve to the real component and the imaginary component. So the real component is VA cosine phi, if we represent it this way. And this is the imaginary component with I here, the imaginary number, VA sine phi. How do we then sum up n harmonic waves of the same frequency? So omega is still the same, okay? So we're going to use phasor representation. But before we go into n harmonic waves, we'll start with 2 harmonic waves first. So we sum 2 harmonic waves. If you look at this resultant then is represented by the sum of E01 exponential I alpha 1, E02 exponential I alpha 2, and the resultant is E0 exponential I alpha. So in terms of a phasor, so this wave at the end of this arrow, we then add on to it the arrow that represents the second phasor, and the resultant would be from the original point up to the end of the second phasor. So that's quite easy, isn't it? Now, if we resolve them, all this into the imaginary and the real component, this is what we have. So for this component, we will have E01 cosine alpha 1 and E01 sine alpha 1. And for E02 exponential I alpha 2, we will have this component E02 cosine alpha 2 and E02 sine alpha 2. So therefore, the resultant then is represented by the real component and the imaginary component, whereby the real component is the summation of this and this. The imaginary component is the summation of this and this. We insert back the time component, and we have then the resultant wave being equal to taking the real part of that. So E0 cosine alpha minus omega t. Then we would want to find out how do we calculate the value of E0 and how do we determine the value of alpha. So let's go to the next slide. Now, if you look at this, it is a triangle. From the cosine law given by this expression that's written here, which is the length of this side squaring it will be equals to squaring of A, squaring of B, and minus 2 times AB cosine of this angle. But if we were to use this complementary angle, which is pi minus C, then we will turn this into a positive because it becomes negative cosine C. Negative becomes positive. As you can see here, that represents over here where the angle we look at is alpha minus alpha 1. Now, if you don't want to do it this way, we can also calculate that using Pythagoras theorem from this one, from the components, okay, the phasor components. Looking at this diagram, Pythagoras theorem will give you that E squaring of this one will be equals to the squaring of the sum of these two and squaring of the sum of these two. That's given here. Expanding that, you have this. Now, this term and this term, sine squared alpha 1, cosine squared alpha 1, these two add up together from trigonometry identity, that's equals to 1. So you get E01 squared plus E02 squared plus 2E01, E02. Then you have cos alpha 1, cos alpha 2 plus sine alpha 1, sine alpha 2. Okay. And this expression here from trigonometry identity again, with that is equal to the cosine of the difference of two angles. So you see, this expression and this expression is the same. And what about the phase angle? Well, that's quite easy. Basically, the tangent of the phase angle is equals to the sum divided by the sum of these two. Then the resultant is written this way. And here it tells us that the resultant is a wave of the same frequency, and the amplitude is calculated from here, and the phase is calculated from here. Now let's extend the two harmonic waves into more waves. For example, let's try with 4. Or rather, over here we show 4. So basically, we represent each wave by the phasor. That's assuming that all these individual waves have the same frequency. So here, this is the first phasor, add on to the second phasor, add vectorially to the third phasor and the fourth, and the resultant would be this one here, from the original point, the beginning point, up to the end of the last phasor. So similarly, if we use n number of harmonic waves, then the phase angle is easy. Basically, it's just the tangent of this angle equals to summing up all the vertical component, taking into consideration negative sign as well when it is pointed towards down, and divided by the summation of all the horizontal component. From Pythagoras theorem, which is easier to use in this sense, rather than the cosine law, then that will be equal to, if you have the summation of all the vertical component and the summation of all the horizontal components of the phasor that makes up the n harmonic waves, then squaring each terms, and that will give you the square of the resultant amplitude. So expanding this, it can be written as the summation of E0I squared sine squared alpha I plus 2 times the summation of the paired vertical components, E0I, E0J, sine alpha I, sine alpha J, whereby here whereby your J component will be larger than I component. And if you expand this term, the second term here, this is what you're going to get. So when you add this to this, we have a term, an expression that will look like this. So from here, now this is common, sine squared alpha I plus cos squared alpha I. This is a trigonometric identity that's equivalent to 1. And over here, this is again equal to cosine of the difference of two angles. So then we can then simplify the expression into this. Here we can then get the amplitude of a resultant wave. Okay, it's quite a simple expression. So let's put it to practice. For example, we have 3 waves, E1 given by this, E2 given by this, and E3 given by this. You note here the frequency is the same. So let's just consider only the phasors. But in order to make it consistent, E2, we rewrite it as 12 cosine pi over 4 minus omega t, and we add a negative 90 degrees. That will give us negative pi over 4 minus omega t. And you know that the sine and the cosine expression is 90 degrees out of phase. So that's why we added a 90 degrees here. Okay, so this is actually equivalent to this. So now we have the common cosine function here. So from the expression that we derived earlier, let's just look at this one here. We sum them up and square them, sum them up and square them on the sine function. So we have sine pi over 3 sine negative pi over 4 sine of pi over 5 and cosine pi 3 plus cosine negative pi 4 plus cos pi 5. Of course, the amplitudes are also inserted. Then you square this term and you square this term. This is what you have. And then you root it, you will get the resultant amplitude, which is 29.67 volts per meter. That is the electric field. Or you can use this expression that we have derived from the previous slide, substitute all these amplitudes, individual amplitudes in, do the pairing of the functions, and then you add them up, and you will come to the same answer as well. And the phase angle is simple. That's taking the tangent of the summation of this divided by the summation of this. And that's just 9.333 divided by 28.166. And the arctangent of this is 18.33 degree. There you have it, the resultant. The resultant wave, then you can write it as the amplitude given by this cosine that is taking the real part of the complex notation of the wave, cosine into, now of course because this is in terms of radians, so you've got to convert that into radians, so that is 0.32 minus omega t. To summarize everything, the sum of n harmonic waves, each of them with identical frequency, will give you a resultant which has the same frequency and the amplitude and the phase given by this expression and this expression. Now let's look at two scenarios. Firstly, the first scenario is when we have n number of randomly phased sources, but they have equal amplitude and same frequency. N is a large number here. And another scenario is when we add n coherent sources. This is randomly phased. This is coherent. They are in phase. So let's see what happens. Let's start with n randomly phased sources. And we have already said that they have equal amplitude. So all of them have E01 and have the same frequency. So as the phases are random, the phase difference between the paired waves are also random, paired constituent waves. And in that case, this term here for the resultant amplitude, we have to take the summation of the paired waves. Since this is random, now summing this random number, which will be randomly dispersed between -1 to +1, well, they sort of cancel each other, and in the end you get almost equal to 0, provided that n is large enough. So therefore this term goes to 0. In other words, now the resultant amplitude is equal to n times square of the individual amplitude. The resultant amplitude is equal to root n multiplied by the amplitude of the individual wave. Of course, we talk about irradiance, whereby it is proportional to squaring the electric field amplitude, then the irradiance will be given by n times the irradiance of the individual sources. So conclusion here is given by this statement: the resultant irradiance of n identical but randomly phased sources is the sum of the individual irradiances. Now n must be large enough. That's important to note. Now for n coherent sources, they are all in phase. So if they are all in phase, their phase angle would all be equal. So the difference will be 0. Cosine of this is 1. Therefore, looking at the expression, the cosine part there is equal to 1, so we drop that. So basically, when you look at this expression, it is actually the squaring of the summation of all the individual amplitude of the electric field. So in other words, E0 squared is equals to n squared E01 squared. So the electric field is equals to n there's the n number of in-phase sources multiplied by the individual amplitude of the electric field. Now, but what about irradiance then? Well, the irradiance now of n identical coherent sources, because they are radiating in phase with each other, would then be equal to n squared multiplied by the irradiance of the individual sources. In this case, it is not necessary that n has to be a large number. We get standing waves when you have two equal waves that's traveling in the same medium, but they're moving in the opposite direction. So one of the example is when a wave comes in and hits the mirror, gets reflected. So the incoming and the reflected wave will interfere and form standing waves. The left as E0 sine omega t plus kx, the reflected wave given by E0 sine omega t minus kx, and we add the phase shift upon reflection. Now, we are choosing sine function for convenience and also writing the temporal part, also for convenience. We write that part first, yeah? And of course, we assume there's no energy is lost upon reflection and no energy is absorbed when the wave's traveling through the transmitting medium. Otherwise, there would be attenuation. Using the principle of superposition, the resultant wave then would just be a linear sum of the two waves. And to simplify in doing the math, what we do is we represent this using beta plus and represent this using beta negative. All right. So adding this to this, it will give us 2 omega t minus phi r. This minus this will give us 2kx plus phi r. And we use trigonometric identity. So when we have a sine of an angle plus the sine of another angle, that will give us 2 sine half beta positive plus beta negative multiplied by cosine of half of the difference between the two. Then substituting this with this and rearranging them, we will then come up with 2 E0. Here we have cosine half of this. So that would be kx plus phi r over 2 and sine half of this. That is omega t minus phi r over 2. Upon external reflection at the mirror, there would be a pi phase shift. So how do we include that into this expression? Therefore, phi r would then be equal to pi. So in other words, we just replace this with pi, which is written here. And when we expand this, we have cosine kx plus pi over 2 minus sine kx sine pi over 2. And expanding this, we will have sine omega t cosine pi over 2 minus cosine omega t sine pi over 2. Now you know that cosine 90 is 0, so this term goes to 0. And sine 90 is 1, so we are only left with the negative sine kx and the negative cosine omega t. And hence the standing wave would then be written as 2E0 sine kx cosine omega t. So this part here is the space-dependent amplitude. All right, so this is how it looks like. We have this light green, which is very pale here, moving to the left, and the yellow one, which can take that to be the reflected wave, equal amplitude, and the pink one is the resultant. You see, it's changing with time. But there are two interesting things that we see here, two features here, whereby at these points, it's always 0. Those are called the nodes. And in between the nodes at this location, the amplitude oscillates, yeah, but it oscillates maximally, and these are called the antinodes. So we ask the question, where are the nodes? Well, in other words, we want to know the location of the nodes. So from the math, from the expression of the resultant wave, the location is the space-dependent amplitude given by this expression here. Nodes are where the amplitude is 0, so we equate this to 0, and that occurs when kx is equals to m pi, and it is substituting for k as 2 pi over lambda that will give us x would be equal to m lambda over 2. So therefore, the position where the nodes are is given by distances of half wavelength. So the nodes are actually separated by half wavelength, as you can see here. Half lambda, 3 half lambda, 2 lambda, 5 2 lambda. At the nodes, you will find that this the amplitude is 0 for all t, because 0 multiplied by this is always 0. And at different time, the standing wave would look like the sine wave of different amplitude. You see is varying in amplitude, but it is always 0 at the nodes. Now, next question is, where are the antinodes? Antinodes occur when sine kx is equals to 1. So therefore, that occurs when kx is equals to or half multiples of pi. So substituting in k with 2 pi over lambda, that will tell us that x will be at m plus half of half lambda. So that will occur when x position is equals to in between those half wavelength, which is quarter lambda. Actually, quarter lambda is here, 3/4 lambda, 5/4 lambda, 7/4 lambda. So basically, from antinode to antinode, they are separated by half wavelength, and the antinode or antinodes lies in between the nodes. And then we ask the question, when do antinodes have maximum value? At all points. Okay. Well, then we look at the time component. So that occurs when cos omega t is equal to plus or minus 1. And substituting for omega is 2 by f. So that is equals to f is 1 over t. This is the period. So we have 2 pi t over period. And when that is equals to m pi, that will give you 1, right? So therefore, at this condition, then ER, the amplitude would be maximum value everywhere. So this occurs when T is equals to pi cancels, you get mt over 2. So it occurs at every half period of oscillation. And then the maximum amplitude would then be equals to 2E0. So when does the standing wave register 0 at all points? Okay, now that occurs when cosine omega t is equal to 0. And we get that when omega t equals to half multiples of pi. So equating this, that will occur when t is equals to pi cancels. Then we have m plus half multiplied by half of the period. That is quarter period, 3/4 period. It should be 5/4 period. So this should be 4 here. There's a mistake here. So what are the properties of standing waves? Well, interestingly, though they are oscillating, they actually used up all the energy to sustain the oscillations between the nodes, so they do not transmit energy. In reality, mirrors, they are not perfect reflectors, and also the transmitting medium actually it absorbs some of the wave energy. So in other words, the wave amplitude will attenuate with distance. So unless you pump in energy, you need a source to continuously replace the lost energy. Then so you need that to sustain the amplitude to remain the same. And because of this loss in energy, then the two waves may not cancel completely at the nodes, and they will not add up also to the maximum of 2E0 amplitude at the antinodes. So the resultant wave will have a traveling wave component, and it carries energy to the mirror and back. If there is a relative phase between the waves, that is, for example, we write this incoming wave and this reflected wave, then you'll find that the cosine and the sine factors in the resultant wave will have the relative phase included into it. Yeah? So it will have a phase angle component, in other words. Yeah. What would be the scenario like? Well, you'll find that the nodes then would be displaced. As you can see, this expression is different now. The nodes will be displaced, but the separation between the adjacent nodes will still remain as lambda over 2. And the times at which the wave is everywhere 0 or when it is everywhere maximum then also will be different from the earlier case. But the principal features of the standing wave, they are not affected. Now, we do get standing wave in laser cavity. This example is relevant for plane mirrors. This is a resonating cavity separated by a distance d. The nodes occur when kx equals to m lambda, right? The EM electromagnetic boundary conditions at the mirror surfaces would require that the amplitude will be 0 at the mirrors. In other words, the standing wave nodes will always occur at the mirror surfaces. We already know before this that the nodes occur at positions equals to half multiples of lambda. This translates to the fact that the wavelengths that get supported by the laser cavity, which is bounded by these two mirrors here, will be restricted and they will have discrete values. So how do we calculate that? Let's look at this. So in other words, we say that the cavity then will be able to support standing wave with wavelengths that must satisfy this condition. That is, the distance between the cavity mirrors must be m multiples of half wave, what we call the standing wave normal modes of the cavity. Okay, so that all this can fit into the cavity length with the requirement of this EM boundary condition. We can then define that the frequencies of the standing modes in the laser cavity will then be determined in this form. So the wavelength of the standing modes are given by lambda m equals to 2d over m from this equation. And relating to the frequency equals to the speed of light divided by wavelength, and we will get mc over 2d. This will give us the frequency of the standing modes of a laser cavity. Now this is valid only for plane mirrors. Here is a sample question. We have a helium-ion laser cavity with a mirror separation of 30 cm, assuming it's plane cavity mirrors, and is capable of supporting laser light of wavelength from the range of 632.8 to 632.802 nanometers. Very small difference here. Let's first calculate the approximate number of modes that the half wavelengths can fit into the cavity. Using the equation that we obtained earlier, is equal to 2d divided by, let's take the first wavelength, that's 948,166. M is equal to that value. Then let's look at the frequency range that's supported now. Here we will have the delta frequency that is supported by the gain medium. That will be equals to C over lambda 1 minus C over lambda 2. So substituting the value, take out the C, and you have 632.8 times 10 to the power minus 9, 632.802 times 10 to the power 9. That will give you 1.5 gigahertz. Then we have another question here, difference in frequency of adjacent standing wave modes. So we will have m plus 1 mode minus the frequency for the mth mode. That will be equals to just C over 2D, and that is equal to 5 times 10 to the 8 hertz. And the next question is the number of standing wave modes that will likely be present in the laser output. Well, in that case, that will be equal to the ratio of the frequency range supported by this gain medium. Divide that by the separation between the standing wave modes. So this divided by this that will give us 3. So the number of standing wave modes that's likely to be present in this cavity would be 3. Here's an experiment visualization using 3.9 GHz microwave. There's a mirror here. So you have an input beam and you can see these waves coming in and then reflected, and it creates standing waves here. So you see the nodes and the anti-nodes. So there's a phase shift on reflection, clear. Next, you can also see standing waves when you have spherical waves interfering. So these are the anti-nodes. So you have the alternating nodes and anti-nodes. Here are 2-point sources that generate spherical waves, and they can produce standing waves. And here I have an example of the 2 sources at different distances. You see the different node patterns here. Okay, can you see that? The learning outcomes for this lecture are listed here. You should be able to describe constructive and destructive interference when considering superposition of waves, and you can derive and calculate the resultant of superposing n number of waves in general as well as for random and coherent sources. And you should be able to derive the standing wave equation as well as determine the spatial and temporal occurrences of nodes and anti-nodes in standing waves. Thank you for watching.